Okay, part 2. We start with a theorem here, 7.14. It's called the principal axes theorem. Whenever a theorem gets a name, it's meant to be important. Plus, just gives us a geometric representation in R2 and R3, so it's fun. Here we go. So let A be an m by n symmetric matrix. Okay, then there exists an orthogonal change of variable that transforms Q of x, which is this x transpose AX, into this guy with no cross product term. So at the end of the last video, we had an example that showed this, and so now we've made it into a theorem that says you can always do this. Okay, so here's the part I'm going to try and get really nice here because it's hard. There's a geometry that goes with this, at least in R2 and R3. R3 is really hard to see because we're doing everything by hand, but R2 is cool. So let's jump right into this. Let's let A be 2 by 2 symmetric matrix, and let C be some constant in R. So what you do is you set x transpose AX equal to this constant. Right, so now we have this thing as a constant. Okay, and I'm teaching Calc 3 right now, and if you guys remember all that stuff, we talk a lot about level curves, and that's actually really what this is in a much bigger sense. So it's more of a projection onto the R2 plane. And what you can show, it can be shown that this corresponds to one of the conic sections, to an ellipse, which you can also have a circle in there, right? A hyperbola. Two lines that intersect. A single point, or no points at all. Okay. So note, if A is diagonal, this corresponds to a conic in standard form. So I'll show you a picture of what I'm talking about here. If it's an ellipse, then in standard form, you've got your major and minor axes on the y1 and the y2. So they're centered here at 0, 0. And so if it's an ellipse, it's going to look like this. I have to use these variables, so it's going to be y1 squared over r sub y1 squared plus y2 squared over r sub y2 squared equals 1. That's the standard form. And this length here, it's called the x radius when you're in xy, but we're using all y's now, so that's the the r sub y1 radius, and then this is going to be the r sub y2 radius. And they lie on these orthogonal orthogonal lines. Now, if A is not diagonal, that implies there's a cross product term, and this thing is rotated. So a similar way might be something like this. Maybe and we have, let me get some color in here. I'm not feeling very colorful today. So let's see here. So here's my shape here. And so my ellipse is off kilter. Okay. It's rotated, in this case, whatever the angle from here to here is. We'll call that theta. And these are called the principal axes, hence the name principal axes theorem. Right? However, finding the principal axes amounts to finding a new coordinate system with respect to the standard position. And well, I mean, y1 is column 1 of P, and y2 is column 2 of P. They're just the eigenvectors corresponding to A. Right? And if you think back to differential equations when we were finding solutions and things like that, you would plot the eigenvectors first, and then those would give us sort of a set of axes to work from, right? Because remember, if we were doing saddles and you had something like eigenvector here and eigenvector here, and this guy went out and this y went in, when we did the shapes, they always followed this sort of so what are these? These are hyperbolas, right? Because you got this box here. And that's one of the quadratic quadratic forms. Okay. So now we classify these things. A quadratic form Q is positive definite if Q of x is greater than 0 for all non-zero x. It's negative definite if it's less than or equal to, less than 0 for all x non-zero. And C, it's indefinite if Q assumes both parities, pos and neg. Right? And this is true via a theorem. A is true, so it's positive definite if and only if the eigenvalues of A are both greater than 0, or greater than 0. Negative definite if and only if they're less than 0, and indefinite if eigenvalues of A are greater than and less than 0. Well, now, let's look at an example here. We'll leave R2 for a second and go to R3. Let A be 3, 2, 0, 2, 2, 2, 0, 2, 1. The question is Q given with respect to this A, is Q positive definite? Right? Well, if the eigenvalues of A are all positive, then yes. But through a little bit of work, you get that they are 5, 2, and minus 1. So it's not positive definite, it's indefinite. And, okay, the classification. Really falls onto A. And so now we say a positive definite matrix A is symmetric for which Q of X is positive definite, right? So and any of the other ones are positive semi-definite. So a positive semi-definite matrix comes from the other two cases. So you have positive definite and positive semi-definite. Okay. So this is more of homework 9. Section 7.2. You got problems 2, 6A, 10, and 26. I already assigned 7.1 in the last 2 videos ago. And so there'll be, I think we'll get through 7.3, yeah, before the homework's due.